Exercise number 18 asks us to verify that the function f of x equals 1 over x satisfies the hypotheses of the mean value theorem on the interval from 1 to 3. We are then asked to find all numbers c that satisfy the conclusion of the mean value theorem. So let's start out here. The mean value theorem has two hypotheses or conditions. Number one is that the function f is continuous on the closed interval in question. You can, of course, look up the statement of the mean value theorem until you have worked with this enough for it to become intuitive. So, is f continuous on the interval from 1 to 3? Well, let's look at our function f and consider where it might be discontinuous. This is a rational function. Rational functions are continuous on their domains. So we need to look for where this function is not defined, so we know something about its domain. Division by 0 occurs when x equals 0, so that is the only value of discontinuity. But 0 is not contained in this interval, right? It's off to the left. So on the interval from 1 to 3, f is continuous, so that checks out. The second condition is that our function is differentiable on the interior of the interval, the open interval, in this case from 1 to 3. We don't require differentiability at the endpoints, as long as it is continuous at the endpoint. Sometimes when we have a continuous function, we take its derivative, we lose something at the endpoint. So the square root function, for instance, is continuous on its domain, which includes 0, but it is not differentiable at 0. It would have a vertical tangent line there. But that's okay. If we lose differentiability at the endpoints, that is entirely okay, as long as we keep it everywhere inside. So to figure out if f is differentiable on 1 to 3, sometimes you can figure that out just by staring at the function, but you might find it useful to actually compute the derivative and examine it. Toward that end, it is probably more useful to write f of x in the form of x to the negative first. We can then see that f prime of x is equal to negative x to the negative second, which is equal to negative 1 over x squared. Checking this function now, we see that once more, 0 is the only value not in the domain. So as long as we're away from 0, the derivative exists. Again, 0 is not in this interval, so f is differentiable on that interval. Those are the only two conditions of the mean value theorem. Rolle's theorem is a narrower statement. There's a third condition that the values of the function at the two endpoints must be 0. But the mean value theorem is more general than that. It doesn't require that condition. Given these two conditions being satisfied, the hypotheses of the theorem, we have the conclusion of the theorem, the statement that there is some number c. There's nothing special about c. It's just some constant. We can call that whatever we want, but c is traditional. Some number c within the interior of that interval, so the open interval from 1 to 3, such that the derivative of the function at c, so f prime of c, is equal to the slope of the secant line connecting the endpoints. So we have f of 3 minus f of 1 divided by 3 minus 1. Or of course you could subtract these in the opposite direction. That's the same as multiplying numerator and denominator by negative 1. The order doesn't actually matter in this case. You're just trying to find the slope between the endpoints. This would be the slope of the secant line connecting the endpoints, and we're saying that there has to be at least one point. There could be more than one, but there has to be at least one point in between where the tangent line is parallel to that secant line. That's what we have there. So let's start computing this, find out what this is. Again, f of x is 1 over x. So f of 3 is 1 over 3. F of 1 is 1 over 1, which is just 1. We have divided by 3 minus 1 is 2. We have several ways we could simplify this. Let's just take the easy route and clear the fractions first. Multiply numerator and denominator by 3. So we get 1 minus 3 divided by 6. That's negative 2 over 6, or negative 1/3. So the mean value theorem tells us that for some value c inside the interval, f prime of c is equal to negative 1/3. We have an expression for f prime of x, right? F prime of x is negative 1 over x squared. So this f prime of c is equal to negative 1 over c squared. And we're saying that that is equal to negative 1 over 3. If we negate both sides and take reciprocals, or equivalently you could do like a cross multiplication, you find that c squared equals 3, which in turn implies that c is one of the square roots of 3. So it looks like we got two values here, which is permissible. Again, the mean value theorem tells us that we have at least one such value. It doesn't tell us any upper bound, but we do have to remember that we're only talking about the interval in question. One of these values is outside that interval. Negative radical 3 is too small. So we only have c equals the square root of 3. Square root of 3 is about 1.7. Even if you don't know that, 3 is between 1 and 4, meaning the square root of 3 must be between 1 and 2. So between 1 and 2 is within that interval from 1 to 3 there. So there we go. The value in question is the square root of 3. That is the only one that satisfies the conclusion of the MVT. For a quick kind of illustration of what's going on here, they don't ask us to draw a graph, but let's just go ahead and whip up something really quick here to kind of illustrate the idea of what's happening. So we have, let's see here, we'll call that 3, which makes that about 2, 1, 1, 2, 3, very crudely speaking. So we have the point 1, 1. We're going from 1 to 3. At 3, we have 1/3. That's about there. Now we have 1 over x, which you remember is the hyperbola that comes through 1, 1, and has the x and y axes as asymptotes. So we have something that kind of, it's going to kind of drop down and sort of level out this way. Okay. Now there is a secant line connecting 1 and 3. And looking at this curve, you can see that at various points along the curve we'll have different tangent lines. Initially the tangent lines are steeper than the secant line, and then they kind of level out and then eventually become shallower than the secant line. At some point in between, we have a tangent line whose slope is exactly the slope of the secant line. In fact, we've computed c equal to the square root of 3, which again I said is about 1.7, so that's somewhere around here-ish. Around here then, looking at that, now my graph is quite crude, so it might not look like a tangent, but the assertion is that if we graphed this accurately, if we graph that secant line and also graph the tangent line at that point, at the point square root of 3, 1 over square root of 3, right here, those two lines would be parallel. That's what the mean value theorem is basically telling us. We have this function that is continuous from 1 to 3. It's differentiable between those values. So there has to be, basically we have this continuous variation along the way. There's going to be a point in between where we have that, that parallel tangent line. So that's what's going on in this problem. There's nothing mysterious about C. For some reason, some students do struggle quite a bit with this theorem. The theorem itself does not tell us what this value C is. Everything after this was just algebra to try to figure out what was going on. The theorem is simply saying that there's some number. Again, we don't have to call it C. That's an arbitrary choice. There's some number inside the interval where the derivative is equal to the slope of the tangent line. And that's about it here. The mean value theorem, like I said, is just a generalization of Rolle's theorem. You might have some questions about Rolle's theorem. The only difference is that Rolle's theorem is a narrower case that only applies when the endpoints, when the function values of the endpoints are both 0. But it's much the same idea.